Hello, everyone, and welcome to this presentation. My name is Marius Bogovici, and I'm going to talk today about Kafka streams and how we integrated that with Spring Cloud Stream and maybe some of the thoughts about running Kafka streams applications in the cloud and in particular with Kubernetes. A few words about myself. I'm currently a chief architect for data streaming at Red Hat. This presentation refers to some work that I did prior to that when I was earlier this year when I was a Spring team member. I'm a Spring ecosystem contributor since 2008, and some of the projects I've contributed to are Spring Integration, Spring XD, Spring Integration Kafka, and as I said, until earlier this year, I've been the Spring Cloud Stream project lead. And I've been personally involved in some of the work that went around Kafka streams. And I'd like to share a few, as I say, a few of the considerations and a few of the thoughts around that. So first and foremost, I like to, this is a 30 minutes is a very short topic it's a very short time for basically covering three major topics in detail. And they're Kafka streams, Spring Cloud Stream, Spring Cloud Data Flow, and Kubernetes. So I'm going to provide kind of a high-level view of these projects, how they work together, how they integrate, and I strongly encourage you to kind of go into the details of each one of these projects and obviously some of the lessons that we learned, for example, especially around Kubernetes, apply to other types of stateful deployments. So I think it's going to be interesting, and I'd like to start by kind of framing the discussion in the context of Kafka streams. So Kafka streams essentially is one of the latest additions. It's not that new. It's been added like a year and a half ago to the Kafka ecosystem, but it's kind of a manifestation of a tendency in the Kafka ecosystem to evolve from a distributed log, a kind of high throughput, low latency message system, and transform into getting closer and closer to a streaming platform. So over time, we've seen adding things like replications and fault tolerance, support for ingestion and for exporting data from Kafka through Connect, support for data processing through streams. More recently, right before the 1.0 release, transactions and exactly once. So there is this consolidation and this evolution from the basic messaging system to a platform. And Kafka streams actually falls into this category. So if you look at the canonical picture that you would paint like 2 years ago, for example, or 3.5, you would look and say, well, Kafka essentially works as a hub between applications that produce and consume data. And here's the question: how do you solve the problem of actually processing that data? Like if you go beyond like scenarios like ETL, data movement, and so on, what do you do? And typically the answer has been either do it yourself, like either just build the logic and then use the producer and consumer API to do that, or delegate to an external cluster like Spark or Storm or Flink. So Kafka Streams is trying to solve this problem from a different perspective by embedding the stream processing features into regular Java applications. That is very close to what we see as the microservice model. Leaving aside the considerations of where do you draw the boundary and like everything else, there is a notion that a complex solution consists of independent running parts that communicate with each other, in this case, over Kafka topics. And you can look at them as black boxes with a number of inbound topics and a number of outbound topics in this case, and essentially have a library that handles data and processes it. And Kafka Streams has basically kind of a couple of interesting features, all of them tightly integrated with Kafka. One is supporting functional transformations through a DSL of its own. So the idea that you can write applications that describe, that take each and every input as an unbounded data set, and you can apply different operators that you should be familiar with from functional programming, like map, flat map, and so on. And you can apply them and create new unbounded data sets is actually pretty powerful. So that's one of the aspects of the programming DSL. On top of that, there are more complex interactions and more complex operators. Some of them involving stateful processing, things like joins and aggregation, right? So it goes beyond simple transformations into actually kind of performing more complex operations on unbounded data set. And we'll see an example very shortly of an application that does, for example, the classic word count example and how it looks like. Other primitives that Kafka Streams provides are, for example, around windowing and reasoning around time. Now, in stream processing, windowing, for example, is a very important concept. So that is, again, reflected into the Kafka Streams DSL. The other part that, and this is very important, and where Kafka Streams has like one of the strengths of the framework is, as I said, the fact that it ties all the stateful processing that goes into aggregation, joining, back into Kafka. All the changes, as we'll see in a moment, are propagated back to Kafka and are coordinated internally by the runtime. So the Kafka Streams is not only the client that communicates with an external system and actually kind of deploys a streaming pipeline, but actually all the computations, all the work, everything is actually performed inside the applications. It differentiates itself by providing one record at a time processing, which means that there is no micro-batching. So every record is treated individually, even if considered as part of a larger unbounded data set. And recently, in Kafka Streams, there's been added support for, as part of Kafka itself, there is support for transactions, and that translates into what they call essentially exactly once processing. What it means effectively is that there are no observable effects as a result of duplicate processing inside the application. So internally, the processor coordinates the consumption of messages and update of offsets. Some important concepts, and they are part of the kind of high-level notions. First, as with any functional programming model, it has to have a representation of the unbounded data set. And in fact, Kafka Streams has two. One is the case stream, which abstracts out a record stream. You can think of it as the logical representation of the data from a topic or data that will get written to a topic. Now, for stateful processing, it's basically looking into, there is another concept which translates the streams by adding meaning to the keys of the streams. As you know, Kafka has, like every Kafka message, has a key value and has a key, a payload, and as of recently, headers. So the key in this case for a K table is basically treated as the identity of the entity that has the data contained in the payload. So essentially, a stream of data is essentially viewed as a stream of updates to a key value store, where the key is effectively the key of the Kafka message. And that is basically, a K table is produced from, for example, from aggregations. Whenever you count, and it's very intuitive, wherever you count data coming in from a topic, it's basically really, you can conceptually think of it as updating a table and observing the results of those changes into an external change set. The K-tables are essentially backed by state stores. So essentially there is a notion that in order to be able to process this data, you have to be able to keep it in a, you have to essentially have access to some materialized views. And these are essentially the state stores. At a high level, how many of you have used Kafka streams before? Okay, quite a few. For the benefit of the other ones, how many of you are Kafka users then? Okay, much more. That's good. So you will recognize, some of you will recognize the example as being the classic word count, right? Essentially what it does is counting words is a series of functional transformations of a stream of data coming in from the words topic that undergoes a number of map transformations through the first through the flat map operator, then the map, and then they're grouped together. And grouping and counting them generates a table that contains, like at least virtually, pairs of words and counts. And on the table, we actually apply the toStream operator, which essentially says, give me the updates to this table and stream them out to the, basically to the topic counts. So in this way, we can count the number of words that have been observed in a specific time window. So there is, if you notice here, there is a time windows argument that contains the boundaries of the time window. So this isn't pretty much it. Like this is in general, Kafka Streams application are like this. Like you can realize, again, I don't want to get into very much detail, but you can realize the model. A number of input topics, a number of transformations, a number of output topics, right? And as you notice here, there are a number of state stores that also need to have their changes propagated and replicated. And the way state propagation happens with Kafka streams is that all these state stores essentially, they're pluggable. So you have different options for storing state in your application. But the strategy is to try to keep as much data as possible locally, but ensure that it is available to be reconstructed in an event of failure. So this is a very, like if you've attended, how many of you have attended Kenny and Jakub's talk earlier about event sourcing? So you will recognize the notion that you are sending down changes, the notion that you are sending updates, and be able to restore them by observing the change flow. In this case, the state that is stored internally by Kafka streams is essentially divided between an in-memory state store, where they're available for immediate access, for fast access, and they are replicated to Kafka as well as a change log. So if an application instance, for example, crashes and needs to restart, then it can access the state that has been stored in Kafka and basically start and restore it. Optionally, Kafka Streams also provides access to local disk. So basically, it can, Kafka Streams application can retain a snapshot locally, which basically speeds up the process of recovery in case the application has to restart, because they don't have to replay the entire Kafka topic again. This is essentially, and as we'll talk a little bit later, especially in cloud-native architectures, this could be a no-no from a 12-factor application perspective. And again, it depends how much data you have to replay in order to restart. But it can also provide an optimization. Like if you're able, like certain deployment models, for example, like Kubernetes, that are more lenient to stateful applications, allow you to mitigate that and give you access to a longer-term persistent cluster. Approaching the problem from the other end. So this is, in a nutshell, Kafka Streams, kind of a general view. How we approach Kafka Streams from within the Spring Cloud Stream and Spring Cloud data flow ecosystem. How many of you are familiar with Spring Cloud Stream? Quite a few. That's good. Or data flow, Spring Cloud data flow, on the other hand. It's not bad. So in this, like if you look at Kafka Streams, and if you look at like the model of Kafka Streams with input and output topics, and basically they're connected through some internal logic, and you look at how Spring Cloud Stream is structured, Spring Cloud Stream follows a very similar philosophy. Describe a number of abstract inputs, describe a number of abstract outputs, have some business logic in between, have a binder, connect them to middleware. Of course, in the case of Spring Cloud Stream, the goal is to make the application middleware agnostic, whereas Kafka Streams is very focused on Kafka. Like there is no way you will connect that to anything but Kafka, right? This has a number of benefits. One is that, of course, the developer has to focus on writing like fewer lines of code. However, the bigger benefit is that if you have a standard application model, if you have a standard configuration model like you have for these binders, if you don't incorporate knowledge about what your target input and output destinations are, and you leave that, allow that to be configured by external configuration, then first you've actually, like you increase decoupling inside the applications and you make them easier to connect together and reorganize in various topologies because you don't have to redeploy a new application. You basically have just to put in a new configuration. And you have different ways of propagating that, right? In our case with Spring Boot. So coming back just briefly to this example, if you're looking here, I'm putting in a lot of assumptions about, like, what if I want to change the topology of this application? What I want to insert something else before or after this, right? Then obviously I have to change a number of applications throughout my system because the destinations and all that information and all other settings are effectively hard-coded in the application. So with Spring Cloud Stream, what we tried to do was to extend and to lend the same configuration, abstract configuration model that we offered, for example, for Bear Kafka or for Rabbit and for everything else, to Kafka Streams applications by saying, look, you only have to describe your K-stream to K-stream transformations or your K-table in between or your joins and whatever you want, and we'll take care of the rest. You describe your problem, you describe your solution in terms of these are the transformations that happen from an abstract input, in this case, for example, called input, and an abstract output called output, and we'll take care of doing everything else. So basically, you write the logic, right? This is the part that you write. It's written completely against the K-stream API. Spring Cloud Stream, in this case, takes care of the configuration options, takes care of creating the stream config using Spring Boot properties, manages the K-stream builder, that builder object that essentially creates the Kafka streams, and instantiates the Kafka binder, which connects, for example, the logical input and output to the words and the counts topic. And we'll see an example of that very shortly. Spring Boot, in this case, what it does, it's basically handling all the rest of this stuff. Externalized configuration, translating environment variables into properties that are actually understood by the Spring Cloud Stream, K-stream binder, providing health monitoring endpoints, and so on. So you basically have like this very encapsulated structure, very encapsulated application, where each of these layers does its job. And as I said, the only focus for you is writing the K-stream, your application against the K-stream API. In terms of deployment, obviously you can take the jar as it is and throw it into, like, for example, you can push it to something like Cloud Foundry, or you can Dockerize, take a Dockerized image and deploy it into something like Kubernetes, or OpenShift, right? Or Mesos, or any other container, any other runtime that supports a Dockerized image. Why? Why do you want to do that? Obviously, when you get the fact that you are able to write independent applications is great for development and is great for maintaining a very cohesive, deployment unit. However, you have to imagine that you have to manage these applications. You have to manage a fleet of hundreds, maybe thousands of applications and instances and nodes that have to talk to each other. You don't want to do that yourself. You want to delegate that to a platform that is capable of running these applications, right? And all these platforms have different capabilities and different expectations in terms of what they can do. Fortunately, for example, if you are following the Spring Cloud Stream model, you can use Spring Cloud Dataflow. Spring Cloud Dataflow essentially has an abstraction that allows you to deploy the different applications to different target platforms. So I've kind of put all these examples here, and then because they are effectively deployers supported by Spring Cloud Dataflow. Once again, you don't have to use Spring Cloud Dataflow for any of this, right? You don't have to use Spring Cloud Stream. But the concept that you will take your UberJar application, for example, Dockerize it, and deploy it to Kubernetes to interact with other applications that are just like that is a very, very powerful one. Is very key in this type of deployment. And if you go to that, just deploying them is just deploying these applications. So is one thing, but you also have to consider other aspects of those deployments. Like, for example, how these different platforms manage state. As I have shown you, the Kafka Streams employs, for example, local disks. Kafka Streams applications are inherently stateful. You can either rely on the failover provided by Kafka, or you can rely on the ability of the application to restart with access to a persistent claim, like it is the case, for example, for Kubernetes. So one quick example and one possible optimizations in this type of scenario with a Kafka Streams application deployed to Kubernetes is this. Kubernetes provides, how many are familiar with Kubernetes stateful sets? So stateful sets are a new, well, not that new, but it's been fairly recent. stateful sets, and this is something that doesn't necessarily apply only to Kafka streams, but I think it's very pertinent in this case. Let's say that we have, like, stateful sets are deployments in which you can specify, in which the assumption actually is that each individual pod in the deployment has an identity, has an index. And this helps you in two ways. One, for example, if you want to know that you are application 0, 1, or 2. Case in point, the broker ID in a Kafka deployment. Like if you want to deploy a Kafka, cluster, for example, it's very useful to deduce the broker ID from the instance index in a stateful set. Stateful sets provide you with something else as well. Stateful sets provide you with, like Kubernetes, for example, and supports the notion of persistent claims, which means that you can associate a pod with basically with a persistent disk. That's not unique to Kubernetes, by the way, right? What is interesting for a stateful set is that what you get for a stateful set is not a persistent disk per se, it's a persistent disk template. So basically what it means that each of these instances in the pod gets its own volume. So word count 0 gets volume word count 0, word count 1 gets volume word count 1, and so on and so forth. What does that mean? It means that these applications actually have access to the snapshots, and those snapshots can be fairly large sometimes. So this could be a pretty significant optimization for your application. So as I was saying, one of the things to consider in this case, especially with Kafka streams, is their stateful nature and how does that play into the deployment. And actually, I would like to just show you real quick the application that I was talking about and how does it actually deploy and run within the Spring Cloud Dataflow deployment. So before we actually end, let me increase the font size, which is always the color scheme. Okay. So this is the application that I had on the slide. This is a Spring Cloud Stream application using Kafka streams. As you see, it has the enable binding annotation of a normal Spring Cloud Stream application, but it uses the KStream processor interface to declare the inputs and outputs. And in the KStream processor, like for the KStream case, the inputs and outputs are actually K-streams. Now, the binder will actually take care of setting up the pipeline, managing the KStream builder. As you notice, there is none of that here. It's just a process method that describes how to process data that's coming in from this abstract input and basically how the data will be produced to be sent to this abstract output named output, right? And this is configurable. As you notice, here, for example, is like we've embedded some configuration in the application. In fact, I don't want to write to a topic input. Sorry, I don't want to read from a topic named input. I want to read from a topic named words. Or I don't want to write to a topic named output. I want to write to a topic named counts, right? So there is this regular Spring Cloud Stream typical configuration pattern that applies in this case and allows me to build that level of indirection. And that level of indirection is also exploited, for example, in Spring Cloud Dataflow. So going for a quick example, I have here a Spring Cloud Dataflow server running in on GCP in Kubernetes. And it has a, as you see, I have all the other services in my cluster. It uses a Kafka. And Zookeeper instance. They're actually installed from some tooling that we actually have some of my colleagues actually have developed a pretty nice set of tools for deploying Kafka in Kubernetes and OpenShift. And what I'm going to do next is deploy a stream. So what I've done here with this application is basically built it, Dockerized it, and deployed it in Docker Hub. And now I have it associated with this word count, with the word count processor name. So what I can do is I have here this stream, word count stream, that is basically HTTP pipe word count pipe log. So as you see, this Kafka Streams application has been deployed as a regular Spring Cloud data flow processor in between the out-of-the-box HTTP and log, like HTTP source and log sync. So let me go and deploy it real quick. So I'm going to deploy the stream. I will create the load balancer for the HTTP endpoint so that we can send data into it. Okay, and you should see the different applications now starting, deployed as pods. This is the word counts. Just waiting for the notification. Let's see the services. Okay. I will copy the URL. I need this address so that I can do a curl post to it. Okay. Maybe I should reduce this a little bit. Let's see the logs. So you see here, this committing task means that the application, the Kafka Streams application is running and waiting for data. And what I'm going to do next is I'm going to post some data to it. Hold on, I had the So what I'm posting right now is just hello Spring 1 2017. I'm just repeating some words and some names and so on. And what I'm expecting is in the log to get the word count. So I think it's going to wait a while because the other pod is still starting. Or the network is down, which is. Okay. This error is basically from Spring Cloud config that it doesn't find. Let me post more data. And if I go to the log, here, you can see some JSON, which is word count, the start and end of a time window. So basically, that is the output of the Kafka streams processor sent to the log. So if you want to take a look very quickly at the topology of this stream, these are the 3 applications that make up my pipeline. 2 of them are not Kafka streams. 2 of them are just regular producer and consumer of data. One of them, in between, is the word count application that essentially is a Kafka streams application. And what you see in the output in the log of this application is effectively the output of this one, which basically that is essentially the proof that it works. So let's just try to send more data again. And I should see the outputs in the log. Unfortunately, there is some noise. So you see the thanks all for attending, every word is counted, and so on. You see also some noise in the logs from the health checks, which is a little bit unfortunate. But this is basically what I was expecting. So this is pretty much, this is what I wanted to kind of show you. It's been a very quick tour of a few major themes. What I want, what the takeaways before we start any questions, or I'm going to be available outside if you want to reach out, are Kafka Streams applications are self-encapsulated, are encapsulated applications running independently. They lend themselves very well to cloud deployments. Spring Cloud Stream provides adds on top of that model by simplifying the way these applications are built, and essentially helps you focus on the business logic. And by wrapping that into Spring Cloud Stream, into a Spring Cloud Stream basically layer, they're actually can be orchestrated by something like Spring Cloud Dataflow. So, happy to answer any questions you have.